already? Okay. Welcome to week 4. Today I will be presenting on Mimblewimble and other spells, primarily Mimblewimble. So the history of Mimblewimble begins in a little over 2 years ago, when the Bitcoin developers had this IRC channel, right? And somebody anonymously comes in the channel and drops a plain text document in it, which is written in English, but the author, the writer, is apparently a non-English speaker, I think. But nobody knows who it is. It's going by the name Tom Elvis Jedusor, which is, in the French translation of Harry Potter, it's Voldemort's real name because it translates to Je suis Voldemort, right? Tom Elvis Jedusor, Je suis Voldemort. This is the English version. If you've seen the movie, right, you know that it does this. You know, he rearranges all the letters. And so, this is a Harry Potter themed crypto system, which is very different from Bitcoin, actually. Like, you may think that, you know, it's like Bitcoin, but it's really not. It's really entirely different, aside from just using proof of work, right? Basically, it's very, well, it's not mysterious, because maybe mysterious is going a little bit too far, but basically it pulled together a whole bunch of different ideas, like confidential transactions, one-way aggregate signatures, in, you know, homomorphic encryption, homomorphic commitments. It pulled all of these together into one system, and it turns out this system may in fact work. The guy who put it all together has not been seen since, but there have other people been working on it anonymously. And so for the past 2 years, they've been working on Mimblewimble. Now, the problem that Mimblewimble tries to solve is, one, the amount of data needed to verify the blockchain. In Bitcoin, you need to download every single block from the Genesis block on down there, so like over 100 gigabytes, just to verify the last few transactions, right? And in addition, you can trace the coins, you can trace every transaction from the Coinbase to every address it's been through, and thereby that makes it hard to preserve your privacy, because if it hits a known address at any point, then your privacy is gone, essentially. And you can tell where it's been. So there are other possible solutions besides Mimblewimble to these problems, which I won't be going into very much. But other solutions are, people have thought of checkpointing, like essentially thought like, well, why don't we just create a checkpoint in the blockchain, and then instead of having to download the last 500,000 blocks, we only need to download like the last 25,000 or whatever. But there's a proof somehow that links it to that main chain. But checkpointing has not been very successful so far in other forms. Ring signatures, on the other hand, are very good because they're really simple, cryptographically speaking. A ring signature is like people combine their signatures, right? They aggregate their signatures into one big signature, and it hides all of their transactions. So it's like, if everybody on the RIT campus like had one credit card, well, you would have no idea who bought like, you know, a pack of gum or whatever, because they are all the same. That's what ring signatures are, essentially. And then you hide the values in different ways as well. Mainly Monero is like the main privacy competitor to other blockchains. But Mimblewimble doesn't use those directly. It uses something that's akin to ring signatures, but not really. They're aggregated signatures. So we'll see. We'll see how it solves these problems quite elegantly. And so there's really only one or two problems that you need to solve for a payment system. One is that if person A pays person B, then person B can spend whatever they got. Right? That's problem number one. Problem number two is, well, how do we know people aren't just creating money out of thin air? In other words, inflation and or destroying coins, that's known as theft, or like, the payment system has to be consistent, right? But in Bitcoin, this is accomplished by all of this being transparent, right? So you can verify this directly. But in Mimblewimble, these properties are hidden, or like that, on the high level, this has to be true. But you can't like go through and see like, oh yeah, person A spent it, and then person B spent it, or you can't be like, hey, wait a second, somebody tried to claim more than their Coinbase reward. No. With Mimblewimble, we don't use all of that data. We simply use cryptographic proofs to say that in the end it all has to sum to zero. That's the core idea of Mimblewimble. Everything sums to zero. Because if it sums to zero, that means there's been no inflation and no theft. Okay? So that's where we get our main idea. So, like I said, there's 4 primary differences. Number one, which is kind of hard to understand at first, is that there are no addresses. Okay? If you want people to pay you in Mimblewimble coins, you don't post a public address on your site or whatever, or you scan a QR code. It doesn't work that way because the blockchain doesn't contain any addresses. It doesn't contain the public keys in a non-hidden form. All the public keys are like submerged. Really, there are no public keys. Okay? There's only private keys which you can use to prove ownership of a value and transfer it to somebody else. But so it uses, like, yes, elliptic curve cryptography is a public key, private key cryptography, but the public key aspect is not used so that anybody can send you money without you interacting with them, right? So in a certain sense, it is like cash, because you have to create transactions interactively, and that makes cold wallet. So I'll go into that later. Sorry, I'm getting ahead of myself. 2 is aggregation. So you can treat a block as one giant transaction. All the transactions get combined together into a block. And in fact, you can cut through. And 4, you can combine multiple blocks into a compact block and use a proof essentially to say, like, all of the intermediate transactions canceled out. So we just have inputs and outputs. So if you think of it like this, right? There's only one marker here. So if you think of it as, okay, we have input 1 and input 2, and then in the next step, we've got, okay, 1 splits into 3 and 4, and then 2 splits into 3 ways. Okay, I'm just going to skip all the numbers. But then, let's say that these get combined into 1, this one goes, and these get combined into 1. Then at the end we have, 8, 9, 10. Mimblewimble, and we'll explain how this works later, it essentially goes, okay, just cut out all of this unnecessary stuff. What we've got is 1, 2 are our inputs, and 8, 9, 10 are our outputs. Now what happened in between doesn't matter. because it'll sum to 0. Okay, that's what aggregation does. Aggregation and cut through. Any questions at this point? Also, all the amounts are hidden. Yeah.
You said the way it knows that nobody stole or cheated is that it all has to add up to 0. But couldn't somebody steal more? Like could people steal in a way that like it all adds up to 0?
Well, if somebody destroys, if somebody destroys 200 coins, but then another person in the same block creates 200 coins out of nowhere, then they sum to 0. So it doesn't matter for us. The net effect is 0. Practically speaking, that probably would never happen because that would require them to, there's no benefit to people trying to do that in concert, right? Because you have to destroy the equal number of coins as you're going to inflate. So if your goal is only destroy or only create, then you can't do that. But if your goal is like, I'm going to create the same amount as I destroyed, well then what's the point? There's no incentive to do that. But, so yeah, it's all nets out to 0. We just know that it's consistent that way. Joe?
You'll get to it probably.
Okay. So, we have a lot of slides to go through. So get ready for some math. Put your math hat on, your wizarding hat, your robes, get your wand maybe. And yeah, we'll prepare. Feel free to try and scribble down notes or try some stuff on your own if you want it, because I am encouraging you to keep track of the math, because this is how we prove that this system works. Okay. So our starting point, of course, is elliptic curves over finite fields. An elliptic curve is an equation, right? It's just a simple equation. You have y squared equals x cubed plus ax plus b, where a and b are constants, right? At any point, any pair of numbers, x and y, that if you plug them into this equation, the equality holds, well, that's a point on the curve. So, in the real numbers, an elliptic curve looks like, so if these are our axes, an elliptic curve looks something like this, or like this maybe, with little 2 parts. But it doesn't really matter, because what we're looking at is not elliptic curves with the real numbers, but in fact, we're looking at them over a finite field. So it wraps around, right? They're discrete numbers and they wrap around. Just think of it as the points are all over the place. There's no way to really figure out how they relate to each other. It's all split up, and there's no. But see, these are so thick, right? That you could multiply this by 2 and end up over here, and then multiply it by 2 again, and now you're over here. So an elliptic curve over a finite field, if the field has the right properties, is a very strong cryptographic system. Okay? And we call this a group. If you put it simply, a group is just like a system where we can treat things like we treat the real numbers. We can add, multiply, and divide them just fine. Okay? So it's a system which is similar to the number systems which we know and use all the time, except that the relationships between the elements are harder to figure out after the fact. So you can't find we'll see, okay, that you can't find the discrete logarithm. This is the key to the security of an elliptic curve cryptography system? Okay, well, I explained, yes. We can multiply points, quote unquote. So yes, the elliptic curve group is a group. Actually, forget what I said about multiplying. You really are just adding them. And multiplication is repeated addition, right? But we can't multiply 2 points on the curve. What we can do is, quote, multiply a single point by adding it to itself that number of times, right? So if we have p, we can find 2p. We can find 3p by adding 2p plus p. And we can find 4p, and so on and so on. Any multiple, we call that scalar multiplication. So when I say multiplication, that's actually what I mean. It's just multiples of a point. And now, so the discrete logarithm problem is this problem. If you take a base point q and multiply it by k, which is a really big number, and you end up with p, then if I give you only p and q, can you find k? You can't. That's why it's called a problem and not a toy or whatever. So this is the basis of the discrete logarithm, is the basis of security for an elliptic curve crypto system. And this is what Mimblewimble uses. Bitcoin uses this for signatures. This is what we're going to use for everything. Okay. We're working entirely within the elliptic curve group. Yeah, I explained this. And then we're going to search for a subgroup of prime order within the elliptic curve group. We're kind of speed through this. So if you have a point P, it generates a subgroup. So if you have like an elliptic curve which has, 50 million points on it, then a single point may generate a subgroup of 10 million points. The order of the subgroup, by a theorem that we have in math, the order of the subgroup has to divide the order of the group itself. And now we want it to be a prime order to avoid attacks on the system. So we're going to, figure out a prime number that's large, but divides the order of our group. And then we're going to look for a point which generates a subgroup of that size. And that's really easy, actually, because you just use a cofactor. Okay, so we can prove that we can do this because if we have, n is the order of our elliptic curve group, then n divided by the cofactor is equal to the prime that we want to find, right? And so if we have a point x and we multiply it by h, if it's not equal to 0, it generates a group of this order, right? Now there's a proof behind that.
You are off one there, right?
I'm off one? Huh?
No, P is the point of, it's the upper second line.
Oh yeah, it should be p equals np plus 1.
Yes.
Yeah. So this is actually p equals np plus 1 because if you multiply n by p, you'll actually get the identity element.
No, NP plus P.
What? Could be, okay, sorry.
It's not really parentheses.
N, okay. N plus 1 times p equals p. Okay, there we go. Okay, there we go. So, but here we're referring to it as p, so, p times x equals the identity element. And then plus p one more time, or no, plus x equals x. Anyway, we want a subgroup of prime order. That's important. And we have the generator of it, and then we find another subgroup that's also prime order, and we have a generator of that. So now we've got two subgroups that are in the same elliptic curve group, so we can add the points together, but they're not necessarily, once we add them together, they're not necessarily in the same subgroup. So what that does is that it gives us essentially two ring is a technical term meaning a group of two operations, but it gives us two systems that, that are separate in a sense, but also compatible. Okay? Because any multiple of, and we don't know the discrete logarithm of them because that would defeat the purpose. So we've got G and H, right? I'm going to erase this part. Erase all of this. So we can start over with G and H, because these are the important things here. Is that we've got a couple of groups, subgroups on the elliptic curve to work with. Now in the paper that I was looking at, it was really confusing, because they kept saying like, oh, we're going to add these two elliptic curves together. But that's just wrong, because you can't add an elliptic curve to another one. You have to add things within the same system, right? Within the same group. So I don't know what they were doing there, but I think they even said like, oh, actually it's a generator of the, yeah, it's the generator. G generates the subgroup G. H generates the subgroup capital H. Okay? Hold on to that. Now, this is the good part. A Peterson commitment is a point which is in this form. Oh, I already wrote it down over there, didn't I? It was here all along. I'll go ahead and just move it over. Oh, we've got C equals R H plus VG. Order doesn't matter because it's a commutative operation. Now V is our value, okay? That is the amount of coins that we're going to send. And R is like our secret key, but we call it a blinding factor. Now C is in the elliptic curve group, right? It's in E, right? Does anybody dispute this? No? Okay, good. I hope you don't, because it definitely is. But is it in G or H? Is it in capital G or capital H?
Now, when you are citing, you refer to this paper, this big paper?
Well, see, this
All
doesn't have enough.
consistently?
It doesn't have enough
So which
information in
one
it.
does?
Right here is where they started getting confusing because
In particular, your hints about this cofactor and what we did here.
oh, I got that from a
Yes,
separate source.
and that's what it looks like.
Yeah, I did.
G and H do really are different groups.
Yeah.
They
They are?
Well,
How does
they
that
can
work?
be added to.
Does that mean that we use the bilinear pairing for that?
I think so.
Okay, well then it just got a whole lot more complicated. But look, this is the part which confused me,
Well, then we have to,
is where they say that G is another generator point in the same curve with H. We call it an elliptic curve, but then we call it a generator point in the same curve with H. That's the part which confuses me.
yet they intersect. Well, yes. No, there is, okay. However, I must believe he did. He just does not really talk much about that. It's how this and this are connected.
These are connected because this is an implementation, right? Grin is an implementation of Mimblewimble.
So what is the corresponding piece of this?
Yeah, it's
Or
here.
maybe, how,
So wait, so what are we talking about?
no, elliptic curves. How much about elliptic curves you went through or here was? Because you see, without doing the basic elliptic curves, the single, the ones which are here, with one tiny cofactor, one prime. First one needs to look at this.
It doesn't
then
have to be
go
tiny.
with two generators.
Two
That's-
two generators of the same subgroup?
Well, you can generate, you can add and enrich the group E.
See, like, this part isn't actually important to the security. This is just what I looked up for how do you find the subgroup.
But here I only you said cofactor, right?
Yes.
This
yes.
H is a small integer, typically,
You should be.
in standard elliptic groups at least, while P is a very large prime, right?
Yeah.
And here, I think the situation is different. Both G and H are large groups, right? These are G and H, yes, they must be large because the logs are.
The H here is not related to the H over there. No.
Right, it's
Sorry.
totally different. H is a small integer here.
Don't- Call this I, okay, sorry.
Well, it is called H in standard.
Well, it's called I, but
Okay.
don't want to confuse it with the generator.
It's different,
It's an integer.
yes.
But does that break anything?
I think it would be healthy to do this basic elliptic curve arithmetic, how you add points to see how the group can be computed quickly, but not backwards.
Yeah.
Have you gone through that at some point?
No, because like I'm just trying to figure out how this system works.
It's hard to, it's very hard to skip
I know.
and
Because,
then go forwards without.
see, because on the one hand we had the bilinear pairing, and on the other hand, this other explanation was talking about them being in the same group. So that is the part that's very messed up, in my opinion.
What is the, okay. I
We
think-
should finish this afterwards, probably.
So,
We should let him keep going.
notwithstanding, we've got some kind of groups here.
We got something going on.
We've got something, and we can add it to something else, and
However, if you put the previous slide, that's telling G, at least I understand, K, this is capital P, right? So this is a point.
yeah, that's a point. P is a point.
This is a point.
G and H are
This
points.
is a point.
Yes,
But this is integer,
those are integers.
and this is integer,
Yes,
right?
sorry.
And I understand it's.
Because like we've got
It's not
integers
just-
and points and then groups. I ran out of
No,
capitalizing.
integers are not. These are not.
Those are integers. K and
Yes,
J.
but they are not in the group.
Yeah, I know, but I'm saying
These
that
are
like,
in the group.
I'm saying that like, if I use a lowercase letter for an integer and an uppercase letter for a point, what am I gonna use for a group?
Middle keys.
No,
Curly.
there are ways to go
Greek
around.
letters.
Anyway, okay,
Greek
sorry.
letters.
It doesn't matter, it's fine.
This is a very
However,
stressful
the
situation.
No, it's fine. Just continue this, it's fine.
But the hint here
Is this
is
okay?
that this is.
Stop blurring out.
It's very hard to find both, so both must be generators, so high order. So
Yeah,
it's
high
hard to
They're high order generators.
both.
Yes, H and J are both generator points.
Going either way, it's infeasible
Yeah.
to find transformation.
We can't find either
one
of these.
into the other.
We can't solve the problem either way.
Right.
Okay.
So you take then expressions of the form GH and VR are whatever integers,
Yeah.
so it's easy to compute C,
Yes, it's easy to compute C.
but given C,
Given C,
nobody knows how to compute V and R. right?
exactly.
It's-
We
So
can
you
go,
have two things instead of one in
this way is
standard
easy,
curve.
this way is impossible,
Well,
super hard.
we call it infeasible. That's a good word.
infeasible.
Because it is possible, it's not true.
So at this point, have we regained our sanity enough to continue?
Yes.
Yes, hopefully. Do we get that using this equation you could find C, but using C you can't find this equation?
Yeah.
Okay, that's good enough. That's good enough for
Now,
now.
I'm wondering, if you really know that that's easy, how would you do that? If say V has 500 bits, you say these are large integers,
Well, yeah, they're really large.
so how would you do that?
No, actually, R is really large. V is not really your choice. V is the value. R is the blinding factor.
But both are large.
No, V doesn't have to be large.
Uh,
R can be large. See, and it hides it. This is what the Peterson commitment does. Thank you for coming. R is what makes it secure.
okay.
Okay, so we're going to continue here. And the homomorphic property of this commitment is we can add V1G plus R1H plus V2G plus R2H. And because of the distributive property, we get V1 plus V2G plus R1 plus R2H. Right? Does this make sense?
Yep.
Yes?
Mm-hmm.
Okay. So now, we're going to use this to say it has to commit to 0. This has to be 0. That is what Mimblewimble, the core idea is.
Well, it has to be 0. V1
V.
plus V2. V.
Here's a concrete example which I think may help. Alice wants to pay Bob. Alice's blinding factor, or her secret key, is A. Bob's blinding factor is B. She wants to send him 25 coins. So what she does is that she does 25G plus, she sends him V and A, so now he has her secret key, and that allows him to spend it by transferring it to a different blinding factor. The blinding factor is the secret information. So she gives him the secret. He uses it to construct this sum, which is 25G plus AH plus negative 25G plus BH equals 0G plus A plus BH. And this is what we call the excess value in Mimblewimble. It's the new blinding factor, the new key. At least,
So both are secret, but you must get it from
so
Alice, right?
B is secret, and so when you add A plus B, that becomes a secret.
Right,
That
so is
only
A.
Bob knows. Only
What
Bob
about-
knows.
What about A?
A, Alice sends A to Bob, so it's no longer a secret to him.
But to everybody else must.
To everybody else, yes. She sends it only to him. It's not published, it's sent directly and securely to preserve the privacy of the transaction.
Wait, so some other cryptographic system is needed aside, right? How can she do that?
It's-
Well, I mean,
But it's just
theoretically-
encryption and stuff.
Theoretically, if you publish A, anybody can then spend it. So in order to ensure that only Bob will be able to make this transaction and get it into the block, she only sends it to him, which assumes some kind of, yes, secure channel.
Separate mechanism, right?
It's a secure channel.
Okay.
Okay, but that's not the thing that we focus on. The thing that we focus on is that they can communicate securely, but in order to transfer value through the Mimblewimble system, they have to interact to create this transaction which sums to 0. Now this whole thing is signed with A plus B as the private key, and it's then included into the block. And we can aggregate these, in fact, we can aggregate these into one big transaction. Now, I'm not going to go through all of the details there, but the idea is you can add up all of the commitments, and you end up with a large commitment. or a commitment which has been aggregated through many transactions. So, if the value at the end is not 0, we will not be able to sign the transaction properly because the commitment is not equal to the private key. Do we understand that? Okay.
Wait, can you explain that? I don't get that.
This is the part that I also had trouble with because they didn't explain it very well. But if I borrow this, so we have an excess value in H, but not in G, right? Because if we commit it to 0 with 0 blinding factor, then we can't spend anything later. Because now we have 0 blinding factor, and it doesn't work. So we need an excess value. Okay, so this is the point where it also gets confusing. It says that because, in their example, they use 85 as the excess value, because 85H is a valid public key on the elliptic curve H, with private key 85 for any x and y, only if y equals 0 is x times g plus y times h a valid public, x times h plus y times g, valid public key in g. The g and h in theirs is reversed because they use g for the,
That's annoying.
sorry. But here we're talking about the value has to be 0, okay? Because if it's not 0, then it's not in this group, right? The commitment is not in this group. Okay. So this is, the signature is part of the transaction kernel, which we're going to use in a minute. Okay. So I'm sorry if this has been just like sort of very confusing, because it is very confusing, and I can't figure out if they mean a bilinear pairing or just two different subgroups. I'm pretty sure that they do not use the bilinear pairing at this point. I'm pretty sure that is not what this is used for, because then it wouldn't make any sense for them to be able to reuse it as, you know, an input to the next transaction. You see what I mean? Because the bilinear pairing is one way. But anyway, this is it right here. Because it has two cyclic groups, G1 and G2. F is a function that takes a value from G1 and a value from G2, and it outputs one in GT, which is actually a multiplicative group. So it's like instead of an elliptic curve group, it's just like a regular cyclic group. Okay? And it has this property, which is linearity. If you multiply one of the inputs by A, the outputs are multiplied by A. Except that technically, since it goes from a additive group to a multiplicative group, the coefficient becomes an exponent. But if they were the same type of group, it would be AP, AQ in the output. Yes. So, now what they use this for, like I said, it's unclear. But I think that they use it for syncing signatures. Okay, and this is the part of the white paper that gets really funky.
Yeah, what?
Okay. Because the syncing signature is this special type of signature what they use. Not just a regular, you know, normal, non-float, or like a floating signature, no. They use a syncing signature, because that's what they call it. Okay. So, okay, I'm gonna try and summarize it like this. Sign, this is the syncing signature. Sign of the secret key in H outputs a signature. Verify takes a public key and an H and a signature, and it just says, true or false. So it verifies, okay. Now the key thing here is that, so H is a positive integer. That's like 1, 2, 3. Now the key here is that verify, given a signature for H, okay, using this information, you can forge SK and H. Given this information, you can forge a signature for SK and H prime, where H prime is less than H. So by syncing, they mean that essentially you can forge a signature for any lower value of H, where H is the height. So it's like the block height, right? This is what we use to compact the chain. It's a